Welcome to the E-Pathshala lecture series in computer science. We are dealing with the course computer architecture. So, in this module we look at what is meant by thread level parallelism, simultaneous multithreading and chip multiprocessors. So, the learning objectives are, we will first of all discuss about the limitations of instruction level parallelism. We will discuss the basics of thread level parallelism, and we will discuss the concepts associated with simultaneous multithreading and chip multiprocessors. Now, all of us know that ultimately we are interested in improving performance. So, in order to improve performance, one of the most important technique that is used is pipelining. So, pipelining, you know, it improves clock speed. It also increases the number of in-flight instructions. And hazards or stall elimination in the case of pipelining is done by means of branch prediction, it is done by register renaming, and it is done by out of order execution and also forwarding or bypassing. So, all these techniques we have already looked at. We have looked at the basics of pipelining, and we have looked at different ways of eliminating hazards or minimizing hazards in pipelining. So, the idea of pipelining is to improve performance, and we have looked at different techniques for solving the problems associated with pipelining. Now, what happens when we try to do deep pipelining? We will first of all look at the effects of pipelining and see how we look at other methods. So, deep pipelining is as you try to increase the number of stages in your pipeline. So, as you increase the number of stages in your pipeline, it obviously increases the number of in-flight instructions. It decreases the gap between successive independent instructions, but it increases the gap between dependent instructions because you have more number of stages now. But depending upon the ILP in the program, there is an optimal pipeline depth. So, you can't make it very small, you can't have too less a number of stages in the pipeline. You can also not think of too many stages in the pipeline. So, there is an optimal pipeline depth that you will have to look at, and it is also tough to pipeline some structures. It increases the cost of bypassing. So, these are some of the characteristics of pipeline, increasing the depth of the pipeline. Now, what happens when you are trying to increase the width of the pipeline? Width of the pipeline in the sense issuing multiple instructions, executing multiple instructions at the same time, so on and so forth. Now, first of all, it is difficult to find more than 4 independent instructions, and it is also difficult to fetch more than 6 instructions. So, because you will have to predict based on multiple branches and all that if you have to fetch more number of instructions. And you will also have to have an increase in the number of ports per structure, because you may have to do multiple read operations, multiple write operations. So, both the read ports as well as the write ports will have to be increased. And if you are trying to issue multiple instructions every clock cycle, you will also have to fetch multiple instructions. And if you have to reduce stalls in your fetch operation, you will have to have better branch prediction, where you will have to find out novel ways of indexing, updating, and avoid aliasing errors. You will have to cascade branch predictors because you will have to look at multiple branch predictions. So, you may have to do a cascading of branch predictors, and you will have to look at advanced techniques like trace cache, where you are not assuming a sequential flow, but you take the actual flow of execution, trace the actual flow of execution across different branches, and based on the actual trace, this actual trace is stored in a trace cache, and you try to fetch instructions based on the trace cache. So, these are some of the techniques that you will have to use if you are looking at ambitiously fetching instructions. Now, in spite of doing all this, there are a lot of limitations to instruction level parallelism. Even though you make your pipeline very deep and you try to go in for multiple issue processors, there are a lot of limitations to instruction level pipelining, taking into account the imperfection of the branch predictors. You may not have everything that hits in the cache. You may have to go in for main memory or the lower level of caches to fetch information. You may have limited number of registers. You can't think of unlimited number of registers. So, all this leads to a limitation in to exploiting your instruction level parallelism. For example, doubling the issue rates above what is available today and trying to go in for 3 instead of looking at just 3 to 6 instructions per clock, even if you try to double it and go to 6 instructions 6 to 12 instructions per clock cycle, you may have to issue 3 or 4 memory operations, memory accesses per cycle. You may have to resolve 2 or 3 branches every clock cycle, and you may have to do renaming and access more than 20 registers per clock cycle, and you may have to fetch 12 to 24 instructions per cycle. Now, all this is too far-fetched, and it is not possible to exploit ILP beyond a certain limit. So, the complexities of implementing all these capabilities is likely to mean sacrifices in the maximum clock rate. So, your clock rate might get extended. For example, the widest issue processor is the Itanium 2, but it also has the slowest clock rate despite the fact that it consumes the most power. So, all this leads to a lot of limitation with respect to ILP. So, though we have looked at increasing performance, that will also increase your power consumption, and the key question here is whether a technique is energy efficient. When it is energy efficient, does it increase power consumption faster than it increases the performance? So, which is the trade-off that you are going to do? Are you going to look at increasing energy because you are also increasing power? So, we basically have to give a thought to all this and come to a conclusion that instruction level parallelism cannot be exploited beyond a certain limit. So, we will have to look at exploiting other types of parallelism. Instruction level parallelism is not the only parallelism that is available. We will have to look at other types of parallelism and see if that parallelism can be exploited. So, the types of parallelism that we are trying to concentrate is thread level parallelism or the data level parallelism. So, we will have to look at whether these parallelism can be exploited. What we are going to concentrate here is the thread level parallelism that is available in your applications and whether that can be exploited in order to get better performance. Now, if you look at a thread is nothing but a process with its own instructions and data. So, the thread may be part of a parallel program of multiple processes, or it may be an independent program. Now, each thread has all its instructions, all its states independently. So, it has its instructions, it has its data, it has a program counter, it has a register state and so on, and it is necessary, whatever is necessary to allow it to execute. That is how you define a process. If you look at data level parallelism is basically performing identical operations on multiple sets of data. So, that is data level parallelism. What we are going to focus here in this lecture is thread level parallelism. So, in the case of ILP, it exploits the implicit parallel operations within a loop or a straight line code segment. Whereas, if you look at TLP is explicitly represented by the use of multiple threads of execution that are inherently parallel. So, we are trying to exploit this explicit parallelism that is available in your application programs. So, the goal is to use multiple instruction streams in order to improve the throughput of computers that run many programs and also improve the execution times of multiple threaded programs. And TLP can be more cost effective to exploit than your instruction level parallelism. So, the motivation behind thread level parallelism is also the fact that a single thread of execution leaves a processor actually underutilized. You may have many of the functional units which are not utilized for most of the time, and just doubling the processor area, single thread performance does not just improve because of that. So, multiple threads, when you look at multiple threads of execution, if the multiple threads of execution share the same large processor, you know that there is going to be reduction in underutilization. So, which means that you are going to have efficient resource allocation. So, that is another motivation behind your thread level parallelism. So, strategies for thread level parallelism, you have two main strategies for thread level parallelism. One is simultaneous multi-threading, where you try to take multiple instructions from multiple threads of execution and you try to issue them simultaneously. That is simultaneous multi-threading. The second one is chip multiprocessors, where you have multiple cores on the same die. Each core probably executes one thread of execution, at least one thread of execution. So that way you have multiple threads of execution happening and you try to exploit thread level parallelism. So basically these are the two strategies for exploiting thread level parallelism, SMT and CMP, chip multiprocessing. We will discuss in detail about these two approaches. So when you look at multi-threaded execution, multiple threads are to share the functional units of one processor via overlapping. So the processor must duplicate the independent state of each thread. For example, a separate copy of a register file, a separate program counter, and for running independent programs, a separate page table. And memory sharing obviously happens through the virtual memory mechanism, which already supports multiple processes. And the hardware for fast thread switch should be there. So this hardware should be faster than the full process switch which happens and which takes about hundreds to thousands of clock cycles, because a process switch is normally a very expensive operation. Now if you are going to do a context switch in hardware, the thread switch or context switch should happen very fast. So you should be able to avoid the overhead associated with thread switching. So when are you planning to switch? When you say that you are going to switch from one thread of execution to another thread of execution, we will also have to decide when you will have to switch the thread of execution. So there are two ways in which you can switch a thread of execution. One method is called fine-grained multithreading, the other one is called coarse-grained multithreading. In the case of fine-grained multithreading, what you do is every clock cycle you try to switch from one thread of execution to another. That is fine-grained multithreading. In the case of coarse-grained multithreading, what we try to do is only when a thread encounters an expensive stall, say for example there is a cache miss, you leave this thread of execution and do a switch to the other thread of execution. That is what is called coarse-grained multithreading. So as I already mentioned, fine-grained multithreading switches between threads on every instruction, every clock cycle, causing the execution of multiple threads to be interleaved. It is normally done in a round-robin fashion. So if I have 5 threads, I will execute the first thread first in the first clock cycle, you will do the second thread execution in the second clock cycle, so on and so forth, and you will continue to come back to your first thread of execution. Suppose if there are any threads that are stalled, you probably skip those threads and do a round robin with the other threads that are executable. And the CPU must be able to switch threads every clock cycle. So the latency associated with your thread switch should be negligible, or you should have a 0 clock cycle latency context switch when you look at fine-grained multithreading. Advantages of fine-grained multithreading is that it can hide both short as well as the long stalls, because instructions from other threads of execution can be executed when one thread stalls. Because anyway you are doing the scheduling in a round robin fashion, you would have also had instructions from other threads available. So you immediately switch over to the other thread of execution. So both long stalls as well as short stalls can be hidden when you go in for fine-grained multithreading. But the disadvantage, of course, it slows down the execution of individual threads, because even though the thread is available for execution, you do not run it to a completion. You just skip the thread and switch on to a different thread every clock cycle. So even though the thread is ready for execution, the thread might get delayed because you are looking at fine-grained multithreading. And fine-grained multithreading is the concept that is used in the Sun's Niagara processor. Now what about coarse-grained multithreading? So if you look at coarse-grained multithreading, unlike fine-grained multithreading where you do a context switch for every clock cycle, here a context switch happens or you switch threads only when there is a stall that is encountered in your thread. For example, a costly stall like an L2 cache miss. So till then you keep continue to executing the same thread. When there is a stall, you switch to a different thread of execution. So the advantages of coarse-grained multithreading is that it relieves the need to have very fast thread switching, because after all it is going to switch only when there is a stall happening. So it is not going to switch very frequently. So you have enough time to do thread switching, and it does not have to slow down the threads, since instructions from other threads are issued only when the thread encounters a costly stall. Of course, when you have a stall getting when thread does not have any stalls, then the subsequent threads will not be taken up for execution at all. That problem is there. But still, a ready thread will not have to stall once it has been taken up for execution. Of course, there are also disadvantages to coarse grain multithreading. The disadvantage is that it's hard to overcome throughput losses from shorter stalls due to the pipeline startup costs. See, unlike fine grain multithreading, where anyway you're going to switch for every clock cycle, you're going to switch to a different thread. So, you would have fetched instructions from multiple threads and you will have them ready for execution. Whereas in the case of coarse grain multithreading, you are going to concentrate only on one thread of execution. So, normally instructions only from that thread are going to be prefetched. So, what will happen is when this thread stalls and you switch over to a different thread, you may not have instructions available for execution. So, you will have to go ahead and go now and fetch these instructions. So, there will be time that is lost in filling up your pipeline. Of course, you can do some predictions and you can try to fill up instructions in your prefetch pipeline, but still that is a problem associated with your coarse grained multithreading. So, the new thread must fill the pipeline before instructions can actually complete. And because of the startup overhead, coarse grained multithreading is better for reducing penalty of high cost stalls where the pipeline refill is far less than the actual stall time. And this is used in this the IBM AS400 architecture. Now, what is the concept of simultaneous multithreading? So, we have looked at fine grained multithreading, we have looked at coarse grained multithreading. Even when you look at fine grained multithreading or coarse grained multithreading, if you are only executing instructions from one thread in a multiple issue processor, you know that most of the time the function, you will not be able to find independent instructions within one thread of execution. So, most of the functional units are going to remain idle when you look at this type of multithreading. So, people looked at what is called the simultaneous multithreading approach. So, in the simultaneous multithreading approach, what we try to do is, for every clock cycle, you issue instructions from multiple threads of execution. So, the insight is that dynamically scheduled processors already have many hardware mechanisms to support multithreading. So, why not use the support that is provided by the hardware and try to exploit the resources in a better fashion. So, what we try to do is try to harness the capability that the hardware has already provided and try to improve the performance. So, we know that you have a large set of virtual registers that can be used to hold the register sets of independent threads. You know that there is register renaming which provides unique register identifiers. So, instructions from multiple threads can be mixed in the data path without confusing the source and the destinations across threads. And it is also possible to do out of order completion, allowing the threads to execute out of order and get better utilization of the hardware. Now, all these features are already available in the processors that we have. So, what we try to do is we try to harness this facility by adding little more to it. So, you just add for every thread you just add a renaming table and keep separate program counters and separate reorder buffers, and the independent commitment can be supported by logically keeping a separate reorder buffer for each thread. So, with just minimal support added to the existing hardware, we will be able to do simultaneous multithreading, where we try to issue instructions from multiple threads of execution in the same clock cycle. So, this is a pictorial representation of simultaneous multithreading. As you can see on the left hand side, you find that there is only one thread of execution. There are 8 functional units available, different types of functional units, load store units, floating point units, fixed point units, branch units, condition codes and all that. So, you have different functional units which are available. So, if you are just looking at one thread of execution every clock cycle, your left hand side shows that you are able to issue 2 instructions, 2 functional units are kept busy during the first clock cycle, 3 functional units are kept busy during the second clock cycle, third clock cycle 2 functional units are kept busy. So, you are able to issue the respective instructions in those clock cycles. say 2 in the first clock cycle, 3 in the next clock cycle and 2 in the third clock cycle. But subsequent clock cycles I do not have any instructions to be issued at all, and then you have other instructions being issued. So, overall the picture shows you that there are many cases, most of the times the functional units remain idle. So, you have not been really using the hardware resources that the architecture provides. So, when you look at simultaneous multi-threading, which has been shown on the right hand side, we are looking at the same functional units. The only difference is that we are looking at 2 threads of execution, and 2 threads of execution we are looking at simultaneous multi-threading. So, you can see that during the first clock cycle you have both the yellow thread as well as the blue thread being issued. So, you have 2 functional units which are kept busy by the yellow thread, or 2 instructions of the yellow thread and 2 instructions of the blue thread being issued in the first clock cycle. Even there you find that there is a lot of hardware resource that goes unutilized, but it is definitely better than the normal multi-threading that we look at. So, this gives you a pictorial representation of the different types of architectures that we have looked at, the multiple issue architectures. The first one shows, the leftmost one shows you a superscalar architecture. Superscalar architecture is basically a multiple issue which can be statically scheduled or dynamically scheduled. So, as you can see, the first clock cycle you are able to issue 2 instructions, second clock cycle 1 instruction, so on and so forth. And in some clock cycles, because you are not able to identify independent instructions, some issue slots go completely vacant. You are not able to issue instructions at all. Now, in compared to a superscalar architecture, if you try to exploit thread level parallelism, you go in for fine grained multi-threading. What happens here is, fine grained multi-threading, you know that you are executing multiple threads of execution, but every clock cycle you are only looking at issuing instructions from one particular thread of execution, and you switch the thread context every clock cycle. So, the first clock cycle you find that instructions from the first thread, blue thread, are executed, issued. Second clock cycle, the ones from the red thread. The next clock cycle you have a yellow thread, next clock cycle you have a a brown thread, so on and so forth. And this is done in a round robin fashion. You have 5 threads of execution shown. So, you have these 5 threads being issued in a round robin fashion. That is a fine grained multi-threading. If you look at the third picture, you find that it is coarse grained multi-threading. So, the blue thread keeps executing till it encounters a stall. Only after that you go ahead and execute the next thread of execution, and when that encounters a stall, you switch to the next thread of execution. Of course, the stalls that are caused in the pipeline because of the pipeline refill that we discussed earlier, that has not been indicated here. We assume that there are instructions available in the other threads of execution also, and that is why no stalls have been shown. Now, compared to these 2 approaches, if you look at simultaneous multi-threading that is shown in the rightmost part of your figure, you find that you have multiple threads combined together and executing simultaneously in the same clock cycle. In the same clock cycle, you find that the blue and the red threads are combined together, the blue and the yellow and the brown threads are combined together. So, that is basically simultaneous multi-threading. And you also have one more diagram which gives you an indication of multi-processing. Multi-processing is you have 2 cores of execution, one core executing the blue thread and one core or processor executing the red thread of execution. Now, these are the various categories of multi-threading. So, having looked at the various categories of multi-threading, we look at the other strategy that is associated with exploiting thread level parallelism, which is basically chip multiprocessing. So, what is the motivation behind chip multiprocessor? Basically, we would like to address the fact as to how to utilize the available silicon. So, you have so much of hardware available, what are the various ways in which you can use this available hardware? Are you looking at making your processor more and more powerful by going in for speculation support, where it's called an aggressive superscalar, or are you trying to look at providing support for simultaneous multi-threading with SMT support or hyper-threading? Because when you look at simultaneous multi-threading with different threads of execution supported in one core, you know that you will have to duplicate a number of registers, your program counter will have to be duplicated, your register state, your ROB, all that will have to be duplicated. So, you are basically increasing the silicon size by going in for these techniques. That is one way of looking at it. The other way of looking at it is, can you look at having several processors on a single chip? So, there are different ways of trying to utilize the available silicon. Are you going to look at just one core of execution, and are you going to make that more and more powerful by bringing in all complicated techniques, or are you looking at several processors on a single chip? That is also another way of utilizing your available silicon. So, now chip multiprocessors basically try to look at the second technique, where a chip multiprocessor is nothing but having several processors on a single chip or several cores on a single die. So, you have the chip multiprocessors which have become very popular now, where you have multiple cores of execution available on the same die, and they may have a shared memory architecture or they may have a distributed memory architecture. We will discuss all this in detail as we proceed along the various modules. And these cores can be homogeneous cores or heterogeneous cores. So, for example, if I decide to have 4 cores on a particular die, you may decide to have all the cores as identical cores, that is called homogeneous architecture, or you may decide to have 3 cores of one type and 1 core which is different from the other 3 cores, that is called a heterogeneous architecture. So, the cores can be homogeneous or they can be heterogeneous, they can have a shared memory architecture or they can have a distributed memory architecture. So, basically CMP, if you raise the question of why CMP, it is basically to handle your wire delays. So, the wire delays get reduced when you have different cores put on the same die, and there is also a diminishing trend towards uniprocessors. There is no point in pushing the processor too far. You can't keep increasing the complexity of the processor. The power consumed is going to be too high, so you can't keep pushing the processor too much. So, you will have to look at other alternatives where you are trying to look at replicating the same core multiple times. And if you look at designing more and more powerful processors, it takes very long design and verification times. So, you look at what is called a single chip multiprocessor. So, a single chip multiprocessor integrates multiple processor cores on a single chip. It eases the physical challenges of packaging and interconnecting multiple processors. This kind of tight integration reduces the off-chip signaling and results in reduced latencies associated with processor to processor communication and synchronization. And CMPs use relatively simple single threaded processor cores in order to exploit thread level parallelism with one application by executing multiple threads in parallel across the multiple processor cores. Even if you have a single thread of execution, it is enough for every core, because even if you look at a quad core processor with 4 cores and a single thread of execution, I can have 4 threads of execution run in parallel. But most of the processors support at least 2 threads of execution per core. So, that way in a quad core processor, you will be able to execute 8 threads simultaneously, and it obviously allows a fairly short cycle time. CMP is an ideal platform to run multi-programmed workloads or multi-threaded applications. However, CMP architecture may lead to resource wastage if an application cannot be effectively decomposed into threads, or there is not enough TLP to be exploited in the application. So, to give you a comparison between SMT, simultaneous multi-threading, and chip multiprocessors, if you look at simultaneous multi-threading, it has a pool of execution units. It is normally a wide machine because you are looking at multiple issue processors there. There are several logical processors where you have a copy of state for each, you have multiple threads run concurrently, and there is better utilization and latency tolerance when you look at SMT. When you look at CMP, they are much simpler cores. There is moderate amount of parallelism. The threads are running concurrently or different cores of execution. So, this is a pictorial representation of SMT versus CMP. You can find that in the case of simultaneous multi-threading, you have multiple threads of execution happening simultaneously concurrently. In the case of CMP, there is one thread running on one core, there is a different thread of execution running on the different core. So, one core runs the thread, the other core runs the yellow thread, but it obviously depends. You can also have two cores of execution, two threads of execution per core, that is also allowed. So, to summarize, we pointed out the limitations to instruction level parallelism. So, in spite of looking at different techniques, both hardware as well as software techniques to exploit the instruction level parallelism, there is a limitation to ILP, and people have identified that it is not possible to issue more than 3 to 6 instructions every clock cycle, even with lots of ILP being exploited. So, explicitly parallel data level parallelism or thread level parallelism has to be harnessed in order to improve performance. You cannot really look at only ILP, we will have to harness your thread level parallelism and data level parallelism. So, we concentrated on thread level parallelism here. So, if you look at thread level parallelism, it can be coarse grained multithreading that you can look at, or fine grained multithreading. We also discussed the concept of simultaneous multithreading. Simultaneous multithreading is fine grained multithreading based on out of order execution, superscalar micro architectures, where different threads of execution are run in the same clock cycle, are issued in the same clock cycle. All this we are trying to look at in order to improve the utilization of the hardware resources that are available. And balance of ILP and TLP is decided in the marketplace. So, depending upon the application that you are looking at, you try to exploit as much of instruction level parallelism available there, and you also try to exploit the thread level parallelism that is available there. Of course, the other alternative to exploiting thread level parallelism is your chip multiprocessors, where the chip multiprocessors reduce the hardware and the power overhead. SMT can yield better single thread performance. CMPs can improve application performance if the compiler can extract enough thread level parallelism. And what is the most effective use of on-chip real estate? Obviously, it depends on the workload that you are looking at and depends upon the compiler technology, so that the compiler technology will be able to extract enough instruction level parallelism. Thank you.